Good morning, 8th graders. So we are going to be talking about the continental drift hypothesis. We'll talk about what a hypothesis is versus like getting to that theory idea. And all that today, talk more about Alfred Wegener, and really start filling in those major gaps of why does this all matter? Why is it that Alfred Wegener is so well known for all of this, and what ideas he had to be able to put it all together. So still working with middle school Earth Science Standard 2-2 and 2-3, and by the end of this you should be able to explain the plate tectonic theory and start to provide some evidence to support it. Construct an explanation using evidence to demonstrate how convection currents drive plate tectonics, and then analyze and interpret data as to how the convection current motion starts playing into plate tectonics, things like that. So make sure that you have your whole group notes in front of you, and we will get going. So we first need to talk about the difference between a theory and a law. So a theory, like we've talked about with like the Big Bang theory and things like that in the past, a theory is something that can't be replicated within a lab setting. It's something that you can't replicate, period. But you're using reliable information to guide your reasoning. It's not just people saying, oh, I think it happened this way because I said so, but rather here's XYZ as far as information to support why this should be the way it happened. Versus a law being something that can be replicated within a lab setting, will have the same relatively way of like concluding the experiment each time. You're going to get similar results every time. On the next slide, just a couple theories and laws that you're probably familiar with. So obviously the Big Bang theory, so the expansion of the universe from one interaction that exploded into what we now know today as our universe. We obviously cannot go back and replicate that, but based off of more and more information that we are still collecting, it supports this idea of an ever-expanding universe. Theory of plate tectonics, which we will talk about for the remainder of this calendar year. And then you have certain laws, like Newton's three laws of motion. A mass at rest will stay at rest unless acted on by an outside force, or a mass in motion will continue to be in motion unless acted on by an outside force. Things like that. You can continuously roll a ball and it will continuously go, sort of a thing, no matter how many times you do it. And then we also have the universal law of gravitation. We know that we don't jump up into the air and then start flying off into space. We know that our planet stays relatively close to the sun within the same orbital pattern, things like that. So yes, you're can't experiment on that, but it hasn't changed in the hundreds of years we've taken the data down on it. So that is the difference between a theory and a law, and it's really important to understand those differences before we move further, because obviously we're talking about the theory of plate tectonics, so it's not something that we're able to 100% prove, but we have enough reliable information to be like, yep, this is relatively how it should have happened. So remember your champ's expectations as you continue forward. It's not that big of a whole group section, so if you are sticking with PowerPoint, then hold on, let's get going. So we've been talking about continental drift, and this is the idea that all the pieces of land once fit together where we formed our supercontinent of Pangaea. And the way that we have been able to start to form that theory is because of Alfred Wegener. He was able to look at different fossils and that are found within, say, all of South America, Africa, and Australia, things like that. So it's well, the only way that this makes sense is if they were much, much closer. Because if you look at our map today, it's oh, Africa and Australia and India are worlds apart, it feels. So how could this be all in these locations? Too heavy to go on the wind, too large to swim across entire oceans, things like that. So Alfred Wegener is the one who started this proposal. So one of my all-time favorite guys, because he was a man before his time. He was able to look at some of these ideas in 1912 and propose that the continents have been gradually moving across the Earth's surface throughout all of history. Because how else would you get different, like the same fossils within 3 different locations that now are hundreds of thousands of miles apart, and all this, but yet you don't find them along, like I could see from Africa to India, kind of, but then you should have fossils along the path there. Australia, if it's always been this island out in the middle of no man's land, there's no reason why you should have similar species of anything there compared to elsewhere. So he was the first person to start proposing this, and he was greatly ridiculed for it. So here is what he started to propose. He proposed that there was a Pangaea, a supercontinent where all 7 continents we know of today were once very much combined. How could he support this? Well, the theory of Pangaea helps support this idea of continental drift, because if the continents were once all part of a supercontinent, and they're still moving today, you would have very similar rock formations. You would have very similar plant and animal life that has been fossilized amongst all of it. Your coastlines, he just looked at the fact that South America and Africa look like they just kind of nudge up to one another and they fit together like puzzle pieces. Things like that why else would it look so similar? And those were the questions he was raising. So, little recap from last time. So let's go back 245 million years ago, where we have Pangaea, or all Earth in Greek, a single landmass, and then about, what did we determine, 65 million years later, it starts breaking up into 2, to where then you have Laurasia and Gondwana, and it didn't stop, obviously, because we no longer have those 2 supercontinents. 225 million years ago, like I said, this is like a timeline today. This is what we had. Pangaea, then 150 million years ago, Laurasia and Gondwana, and then 100 million years ago or so, you get the 7 different continents finally starting to make it into what is the correct location. And then today, obviously, we have the Earth as we know it, and we're able to start to measure and monitor and see that things are still moving. We're able to now start to support it with actual scientific data because we have the technology in order to do so. So again, just this visual representation for you. I wanted to make sure that you had this again so that it's when I start saying like Gondwana and Laurasia, you knew exactly what I was talking about. So here are some of the clues that Alfred Wegener was taking a peek at. So climate, fossils, rock clues, and the fact that there are many different continent shapes that revealed patterns of their past locations relative to one another. Again, that South America to Africa sort of buddying up. So let's talk about each of these a little bit more in depth. So climate clues. We obviously know that climate has changed. It's changed just within the last 50 years significantly. But the way that we can tell that something has gone on is we now look at where like our ice sheets would have been during the Ice Age. We can physically see within our rock strata sediment deposition or deposited by glaciers and sheets of ice were the same in many continents. So yes, we know that here in North Dakota we had a giant ice sheet and glacier over our land, and it followed down the Red River Valley. That's why we're so flat. But you had similar sort of glaciation, not just amongst North America, but also into Europe and Asia. And the fact that they're so similar with similar sediment depositions, there is no reason why that should happen. Yes, sand travels in our air. Over on the coasts, depending on which way, typically I want to say it is from east to west, we sometimes get Saharan desert sand, and that's just because of how large the jet streams are. But this, that's like itty bitty little sprinkles now and there. This is like you dump an entire sandbox across two major countries that are now separated by an entire ocean. So it's more than just a little bit of sand. This is like similar soil compositions between North America and Europe. We also get things called glacier grooves. Again, this is why we are so flat here in North Dakota. So the glaciers move across the land and flatten it out. And if you were to take a pencil and go across a piece of paper, it stays fairly similar. You take a different pencil and do it, it makes different markings. But then that one stays consistent. So the fact that we can see glacial grooves, again, among two separate continents, there's no reason why that should be the way that it is. And then it proved that the continents are not in the same location that they used to be. They actually used to be much, much closer. Again, the idea that there's so much similarity. The one thing in science is nothing is ever 100%. But if you have enough similarity, you start to make those connections to where you say, okay, here's a new idea. Here's your new hypothesis. So there you go for climate clues. Fossil clues. These are like my all-time favorite. I love looking at fossils. We have fossilized tropical plants that are found on multiple continents. Now, that not so much like, oh, seeds can travel, birds and other animals eat them and then deposit them through their feces and things like that. Like, you're like, whatever, not a big deal. Here's where it becomes a big deal. We're finding these tropical plants fossils, not just on South America, Africa, and Australia. We're finding them in Antarctica. And obviously, as we know, Antarctica today, it is a giant ice sheet. There is no reason why they should have tropical plants. I can't even keep a palm tree alive in my bathroom. I can barely keep my snake plant alive in my office. So why would we have fully developed fossils such as this picture? So that plant had time to flourish and grow. Why would we have that in Antarctica? So those are the things that we start to take into consideration. Okay, well, how would Antarctica have been able to support this kind of life? Well, it couldn't have been down at the South Pole. Nowhere near it. It had to be much, much higher in latitude, or lower in latitude, I guess, technically. Yeah, because they're 90 degrees south. So like closer to the equator, where it had to have been much, much warmer, had to be much more wet, and be able to support that kind of life. This kind of life survives in our tropical climates around the equator, and going no further than 60 degrees north or south. Excuse me, latitudinally. It doesn't work. We don't have these kind of plants native to North Dakota because we're too far north. We get too cold most of the year. So those were the kinds of fossil clues. And on top of plants, we're finding like large species of reptiles. We don't have much for reptiles up here, nor do they down towards the South Pole. Just saying. And their bodies are so enormous that there is no way they could have sustained that sort of a migration over an ocean. It just is not physically possible with what we know about larger reptilian animals these days. Then rock clues. Everyone's like, why do you like rocks so much? It's because they're so cool and they tell us about our history. We have mountain ranges and rock formations that have been found on different continents that we can only then assume were once created at the same time. So if you look at rocks in South America and rocks in Africa, they are relatively the same age, and of similar chemical composition. We have talked about how we can identify rocks through different chemical analyses and things like that. And this is essentially what we've done, because we can look and we can see the Andes Mountains are relatively the same age to, I can never remember the actual name of the mountain range in Africa, but relatively the same age. Just like we can look at the Rockies and determine that the Rockies are much, much younger than the Appalachians. The Appalachian Mountains over in the east are very much more rounded, versus the Rockies still have those points. The only reason why they get so rounded is because of long-term weathering and erosion, versus the Rockies still have points to where they haven't been eroded nearly as long. So we can determine that they are much younger. They formed much later in Earth's history than the Appalachians. So those are the sorts of things, granted far more scientific, that geologists are doing to identify how things in South America and Africa now line up. Speaking of Appalachians, we are also able to identify that the Appalachian Mountains and the Caledronian Mountains over in Europe also formed around the same time, and they actually pulled apart from each other. So at one time they collided to form this mountain range, but then basically were ripped from one another, and that's why they have like these weird faces on them. And by faces, I mean like flat surfaces that seem to line up. Again, different weathering patterns make it a little more challenging, but very, very similar. So those are the kinds of rock clues that geologists have been using to identify how the Earth may have looked hundreds of millions of years ago. So Wegener's ideas were highly questioned. His theory wasn't widely accepted. He looked like an absolute madman, saying this is how the Earth looked and things like that. And that's because we didn't understand the forces causing the movement. We had no idea about convection currents back in 1912. To where he's like, I know this is happening, but I don't know how. Okay. It's very similar to like if you go and try to defend yourself with your grown-up and they're like, well, prove it to me, show me. And you're like, I don't know how to prove it to you that I'm telling the truth. Things like that. That's essentially what he did, but on a grander scale. You're just arguing with your grown-ups. He was arguing with the world and the scientific community. And on top of it all, here's why I love Alfred Wegener. He was not a geologist by trade. He actually went to school to be a meteorologist, and back then being a meteorologist was like a soft science. It wasn't something that respectable men did, because why can't you just look at the like sky and say, oh, it's cold outside, it's gonna rain, things like that. But he was so adventurous. If you have an opportunity, please watch the little biography that I added into the video notes, because it explains his life so well and explains why I think he's absolutely so cool. Man literally died in Antarctica, and his wife said, leave his body there, because that's where he wanted to be. He made multiple explorations to Antarctica to try to prove his theory. So, sorry, sidetracked. So we weren't able to actually start to answer those questions until the 1940s, when World War II was going on, and we developed the sonar that made it possible to see seafloor spreading occur. And it wasn't possible to measure the speed of the continental drift at that time. We didn't know that it moved millimeters at a time. Like, he knew it wasn't moving quickly, but of course everyone's like, well, how slow is it, sort of a thing. And it's like, well, nothing's changed in my lifetime, because you don't notice something over like less than 100 years. That a couple millimeters each year for 100 years isn't very much, and especially if you didn't know where it started, sort of a thing. So he was essentially written off as a madman. He was not respected until the 1940s, where he finally received his accolades. because we had the last missing piece to start filling in his puzzle. It sounds really lame, but it's like, wow. It's like Picasso. He wasn't like honored until after his death, and it's like, it's so unfortunate that it takes that, but it takes newer technology in order to support a lot of ideas that scientists have. And back then, because the world was so new and so unknown, no one really could like stand by him and be like, yeah, we'll eventually find out why and all this, or we'll find out why it isn't, sort of a thing. That's just not how they were, because they didn't want to be ridiculed and mocked for believing similarly to a crazy man. So finally we got our answers in the 1940s, where we were able to start to explain how the continents drifted and the origins of why do we have volcanoes? Why are there earthquakes? Why don't earthquakes happen everywhere? Why are they happening only along specific areas? We are able to determine mountain ranges and why we have those. And especially like you look at the Rockies, they're in the middle of a continent. Why? Things like that. The knowledge of convection currents and the plastic-like asthenosphere finally helped answer those questions of why is this happening? Because we didn't know things below our feet were actually moving. Because to us, we see our soil, we see our crust, and it's a solid thing. So how could our planet not be solid all the way through? Those sorts of things. This is why I've really enjoyed learning about this kind of stuff, because it reminds me of being able to it reminds me of feeling like I can't support my ideas, but eventually you'll have enough data and enough of the correct terms and things like that to be able to truly express how you feel and what's going on. So that is how the plate tectonic hypothesis came about, that eventually was able to be turned into the plate tectonic theory. It was the hypothesis up until we had the answers, until the 1940s. And then it finally was looked at as a theory. And moving from hypothesis to theory is huge in the scientific community, because it finally says your research has paid off, to where everyone now knows this. Sort of the thing. We teach it to 8th graders in the middle of North Dakota, those sorts of things. So yeah, that's kind of what's going on. If you have any questions, please feel free to reach out. I want to answer them to the best of my abilities. Like I said, I highly recommend watching the little biography. It's like less than 10 minutes on Alfred Wegener in the video notes. Yeah, awesome. Any questions, let me know. There is an exit slip that goes with this. So once you're done with your notes, please come and receive that. Thanks, guys.